Welcome everybody to the fourth part of the third week in the OpenHBI course Parallel Programming Concepts. We meanwhile discussed different approaches to express your intended level of parallelism inside your application. We talked about the creation of threads, and we also talked about the definition of potential tasks, and we also talked about the idea of expressing high-level parallelism as part of a functional programming approach. In this unit, we want to show you one example for a language that is able to combine all these different concepts into one language. This is the Scala language. This is also a precondition for a discussion of the Scala actor concept we will do in week number 5. So what is Scala? Scala is a modern language that is an example for the combination of the object-oriented world concepts and the functional programming world concepts. So Scala serves as an extension of Java syntax, so it's very familiar for Java developers, but it has the potential to allow you different ways of expressing your concurrency in the code. In Scala, expressions, statements, and blocks are defined as in Java, so this is a thing that you may already know if you have experience in that language. Every value in Scala is an object, which is a difference to traditional Java, where we sometimes have primitive types, and every operation is a method call. So this is more or less a more strict definition of an object-oriented language. In Scala, we have functions as first-class concept. So as we heard in the last unit, there is a possibility to define higher-order functions, where the argument of a function call is another function, and this allows the higher-order function to perform some kind of operation that is handed in by the calling code or calling activity. In Scala, the programmer has a very unique choice. He can actually choose how to express concurrency. Either the developer wants to use traditional concurrency expressions as he knows from Java, or he may want to switch to a purely functional approach. Both things are possible in the same language. You can also mix and match. So Scala is a very good way of dealing with concurrency and different levels of knowledge in the developer world. You can take an existing Java example, you can easily move it into the Scala world and then start to optimize the different parts, maybe for better concurrency behavior in order to exploit your parallel resources. The Scala compiler will take your code and compile it to Java Virtual Machine bytecode or .NET bytecode. So whatever you produce in Scala can then run on a classical Java runtime or .NET runtime, which is also an advantage if we talk about developing parallel programs for business cases. Most language constructs in Scala are library functions. They can be overloaded. This is also done in reality, so a lot of stuff is going on in the Scala development with respect to new concurrency primitives, new communication paradigms for shared nothing systems. And the whole flexibility in the Scala language and the syntax leads to the fact that there are several very prominent examples about companies moving to Scala as one of their primary solutions. One example was Twitter in 2009, where the company was migrating some of their codes to Scala in order to get the rich expressiveness of the language and the syntactical possibilities in the code. So when we take functions as the most interesting point in the implementation of Scala, the idea of having functions as first-class language construct, the question is, how is this expressed in Scala? And here we see an example how this works. You see that we have a function definition for sum up range. This is a function that is expected to sum up all values from A to B, and it's implemented as a so-called tail recursion call. So we see here that the input parameters are taken, and then we do a recursive call to the same function at the end in order to sum up the remaining values. So sum up range in itself takes also a function as an argument, and this is only done in order to apply this function that is handed in to the values before the actual sum operation takes place. When we take this idea, then sum up range becomes a higher order function as introduced in the last unit. So we can now write different kinds of mapping functions that translate our input values into something else before the actual higher order functionality takes place. So here we see that we either have summing up the pure values. In this case, we would hand in an identic function that just takes an input value and returns the same value, but we can also implement something like the sum of all squares easily. This is done by defining a square function and handing in this square function as part of the higher order function call. So here you see a nice implementation of this functional programming paradigm, which allows the sum up range functionality to now do any kind of optimization. For example, sum up range could now decide splitting up the work into different tasks and spawning them on different processing elements so that some kind of parallelization takes place that hopefully speeds up the overall computation of the range sum. Scala has also all the other functional programming paradigms or syntactical constructs you would expect in such a language. For example, we find also anonymous functions here. So we can take the same example and write it even in a more condensed way by leaving out the type declaration and also by leaving out the explicit function declaration. So you can end up in very short, very condensed code if you want that, which still gives you the possibility to have a high level of concurrency hidden inside the implementation of the higher order functions. The interesting part of Scala, as I said, is the language flexibility, so that you can decide if you want to have a pure object-oriented, a pure functional approach, or something in between. In order to elaborate this example a little bit more, here is something from the Scala tutorial. So we have an implementation of the well-known quicksort algorithm. The first version here is a recursive one, which is traditional style, how we would find it in other imperative languages too. So we have our sort recursive call, and our sort recursive call then performs a recursive sorting operation after the quicksort principle based on the pivot element. Some interesting points for Scala syntax are here functions in functions and the definition of immutable values with the val keyword, which is also a precondition for functional programming. If we now take this example and simply rewrite it again in Scala syntax to have a more functional style, it would look, for example, like this. So we have again a sort function, but in this case we use support from the language libraries in Scala for functional statements such as the filter higher order function. So the filter higher order function takes a predicate function and applies it to all the different values for filtering. So what you get at the end is a reduced set of elements as a result from the filter operation. And here this is used in order to filter out the elements that are either larger or smaller than the pivot element, which is the typical operation we need in quicksort. So if you do this kind of programming, you give the Scala runtime and the library a chance to parallelize your work, because the filter implementation may now decide to express the activities that have to happen on the data array as concurrent tasks, and then the task runtime library can decide to map these tasks to different threads on your processing elements. So working with these high-level primitives gives your runtime system a chance to hopefully parallelize your work automatically, as long as you have side effect-free functions, which is given in this example. If you don't like the functional programming style of dealing with things, Scala also gives you the classical Java ways of dealing with concurrency. So we have a monitor implementation in the Scala objects. Scala AnyRef, the base class for all objects, has the typical monitor functions. We have again the notion of synchronized blocks, where we saw them already in the Java version of monitors, where you are able to define that in several functions inside a class, only one of them should be executed at a time. We have futures, reader-writer support, semaphores, so a lot of constructs that are well known from classical thread parallelism or even task parallelism. There's also support for spawning tasks. And there's an additional concept which we will later talk about in week number 5, which is the actor concept. And this directly targets shared nothing environments where you want to have a standardized way of communicating between processes that do not share a common set of memory. When we say that Scala has all the different things we already talked about in one language, then the question is, what about parallel collections? And the message is also this is supported in Scala. So you have concurrent hash maps, concurrent sets, all these different data structures that do the synchronization by themselves based on their member functions. Scala also have iterator support, so you can use something like a for each statement to go through a collection of data items and apply some kind of activity on each of the items. Again, here the Scala compiler and the runtime system has a chance to automatically parallelize your work. So it depends on the kind of data structure you use in here, wherever the runtime will try to run your different iterations in parallel or not. The only remaining relevant message here is that if you use these functionalities, you still have to make sure that you don't introduce race conditions by yourself. So you see here in the example, although we rely on high-level primitives on a very high level of abstraction, there's still the possibility for having race conditions because the shared variable sum is not considered in the synchronization. So using high-level primitives, using functional programming style, using all kind of abstractions doesn't actually save you completely from thinking about race conditions. If you thought about that, there's a relatively easy and nice way to prevent them, but they can't be ignored at all. The only way to deal with that in a way to ignore it completely would be a shift to pure functional programming, which may or may not be relevant for your particular application environment.